Hi guys, and welcome back to my channel. In this video is going to be the first in my Atkins lecture series. And in this video, we're going to be talking about the birth of quantum theory, why it sort of was motivated, and why classical theory was failing. So let's get right into it. So first, I want to discuss a little bit about the history of the development of atomic structure. And this will sort of lead into our next video in particular when we talk more about the Bohr model of the atom. But I just want to give an idea for the key experiments that sort of led up to that, the model of the atom we have today. So one of the first main experiments was J.J. Thomson's cathode ray experiment. So this diagram here shows the setup of the experiment. He was studying specifically cathode rays, he took these cathode tubes, which were like glass tubes that were evacuated of all materials, and applied a massive voltage across these glass tubes. And what happens when you apply a really big voltage across something is electrons will jump through the tube because of this voltage, because of this applied sort of electric field. So what happened was he created basically an electron source, which is called our cathode ray, as you can see in the diagram. So these electron sources were put between a sort of magnet, and the magnet creates an electric field. A magnetic field. But magnetic fields interact with charges. So magnetic fields interact with charges, and this causes the charge to curve. So as you can see in the diagram, the electron beam is sort of curving in this direction. The direction of the curvature depends on the sign of the charge. So based on this, he was able to tell that this cathode ray was made up of negatively charged particles, and thus he discovered the electrons. Also, based on the amount of the curvature of the ray, he was also able to determine the mass to charge ratio of the electrons. So this was really interesting and was a huge development, and one of the first subatomic particles that were actually discovered. The next big experiment was Robert Millikan, and this is called the Millikan's oil drop experiment. You might have heard of this in AP Chem. This experiment determined the charge of the electron. So Thomson was able to determine the mass to charge ratio, but Millikan was actually able, with Thomson's information, to figure out what the exact charge of the electron was. So in this diagram here, we can sort of see the setup for this experiment. He had oil droplets, and these oil droplets were not neutral, so they were electrically charged. He put them in between these two plates, which had a difference in voltage. And this means there was some sort of electric field between the plates, right? And this electric field causes a force on charged particles, and the charged particle in his case was the oil droplets. So these oil droplets would have a balance between an electric force that was pointing up and a gravitational force that was pointing down. And what does that mean, right? If you have an electric force balancing out the gravitational force, when that's true, we can figure out what the charge of the oil droplets was. And so based on this, he was then able to find the charge of the electron. So Thomson was able to find the ratio, and with Thomson's information, Millikan was able to find the charge. The last huge discovery was by Rutherford, and this is his famous gold foil experiment. He was the one who discovered the nucleus, basically, and this was a really important discovery because before him, scientists thought that the atom looked like something like plum pudding, where there was sort of a sea of positive charges, and the plums were like the electrons. The electrons were sort of floating in the sea of positive charges. Rutherford's discovery sort of made that sort of obsolete, because now he said, no, all the positive charge is concentrated really tightly in the nucleus, and most of the atom is actually just empty space. So let's look at what this experiment was and why it was so revolutionary. So here we can see, right, there's a gold foil, that's what Rutherford had, and he shot these alpha particles, and alpha particles are just helium nuclei. And these alpha particles are super penetrating, right? So for an analogy, they're basically like a bullet, and your gold foil is like a piece of tissue paper. So you would expect every single alpha particle to go straight through this tissue paper really, really easily. And that's sort of what he observed. Most of them passed straight through. But what was really weird was that a few alpha particles were actually deflected back. And this was sort of really, really unexpected, right? It's like if you shot a bullet at a tissue paper and somehow it bounced back at you. So what does this mean? This means that there must have been a super high positive charge density for this deflection to happen, right? This is a nucleus, so it's protons and neutrons. And only if this hit some other super high charge positive density, such that the electric force was so strong that it repelled it and it was deflected. That's the only way that an alpha particle could be somehow deflected back. And this is how Rutherford sort of discovered that this positive charge density must be super high, and that's how he discovered the nucleus. So this was a really interesting and powerful experiment that sort of changed how we thought atoms were like. And this all eventually led to the Bohr model of the atom, and finally the Standard Model, which we use today. Now let's talk a little more about quantum theory, and not just about quantum theory, but why classical theory was failing, right? So let me define exactly what I mean by classical theory. So what exactly is classical theory? This is basically the theory that Newton and Maxwell had sort of laid in stone, and physics was sort of based on for the past, 200 years at this point. So Maxwell believed light is just an electromagnetic wave, and Newton was F equals ma, and what Newton had in mind was that if I know the position of a particle right now, and I know its initial velocity, and I know all the forces that are acting on that particle, I should know at any point in time where this particle is going to be and what speed that particle is at, right? So it's sort of this certainty that you have with classical theory that you don't have with quantum theory. Oddly enough, right, we discovered the flaws in classical theory when we had to look at blackbody radiation. So let's talk about a little bit about blackbody radiation, and first let's define what exactly is a blackbody. A blackbody is an idealization, and it's something that absorbs all radiation and emits all radiation in a continuous spectrum, and it doesn't favor one wavelength over another to emit or absorb. A really good example of a blackbody is a star. So a star basically absorbs all radiation and emits all that radiation back, and it doesn't reflect anything. But a star is not a perfect blackbody because of absorption lines, and we'll talk more about absorption lines in the next video. But just to give a little heads up, right, a star has hydrogen in its atmosphere, right? And what this hydrogen can do is when the star emits energy, this hydrogen will absorb certain frequencies of light, and this will change the electron's energy level in the hydrogen. And this absorption creates dips in the star spectrum. And we'll talk more about this, but this is basically why it's not a perfect continuous blackbody spectrum. But a star is a very, very good example of something that's very close to a blackbody. When we talk about blackbodies, there's two key radiation laws that are really crucial to understanding blackbodies and their properties. The first law is the Stephen-Boltzmann law. So let's talk a little bit about this. This law relates the power of a blackbody to both its surface area and the temperature the blackbody is at. So as we can see with this law, power is proportional to the surface area, and it's also proportional to the temperature to the fourth power. And these sort of proportionalities are really important. And this area is the surface area of the blackbody. The other factors in the Stephen-Boltzmann equation is the emissivity factor, and this basically tells us how much of a blackbody is the object we are looking at. So if the emissivity is 1, we have a perfect blackbody. If the emissivity is 0, we have something that reflects all light and doesn't absorb anything. Sigma is our Stephen-Boltzmann constant, and it's basically a proportionality factor, and it's not very important to memorize. Now let's look at Wien's law. This is the other key law when we're looking at blackbodies. It relates the max wavelength, the wavelength that our blackbody emits most at, to the blackbody's temperature. And we can see that T times our lambda max equals a constant. This means that T and lambda max are inversely related, right? So let's take an example, right? Think about a star that's red. That means our lambda max is relatively high because the max wavelength, the wavelength that it's emitting at the most, is red, which is a high wavelength. So that means our temperature of the star must be sort of low, right? And this makes sense with intuition. Now, if we think about a blue star, that means lambda max is relatively low, which means the temperature must be high. So just this inverse relationship is good to know. These two laws were actually experimentally determined. And weirdly enough, classical theory could not explain this. And when we tried to explain black bodies with classical theory, we ran into this thing called the UV catastrophe. And what was this UV catastrophe? It was basically that classical physics said that all black bodies, really no matter the temperature, even low temperature black bodies, should emit strongly at high frequencies, like UV, X-rays, and even gamma rays, radiation. And this is clearly not true. It would be detrimental to everything. So we needed a theory that matched up a little bit more with reality and the obvious reality. And this was where quantum theory really started to shine. So let's talk more about Planck, and he was really the pioneer of quantum theory. What exactly did he do? Right? Planck took the approach that electromagnetic radiation was quantized, and he said the smallest amount of electromagnetic energy is given by a photon. So one photon is the smallest amount of electromagnetic energy you can have. And the energy of a photon is given by this equation, where you have the energy equals Planck's constant times the frequency of the light. So basically he said that energy is actually delivered in discrete packets. There's not a total continuous spectrum of energy. There's these discrete photons that deliver discrete amounts of energy. And this sort of changed everything. So how does this fix the UV catastrophe? Let's just give a little bit of intuition, because the math behind it is fairly complicated, but some intuition is really good to have. So basically he said that a radiation of frequency mu, right? Say we have radiation of frequency mu. This requires a minimum energy to start oscillating. So if we think of some sort of oscillator and we want it to radiate at a frequency mu, Planck said there needs to be some minimum threshold energy in order for this oscillation to happen. He then said that low temperatures, right? Say I have a low temperatures do not have this minimum energy. So large amounts of this high frequency radiation like UV, gamma, and X-rays cannot be given off. And this basically solved the UV catastrophe. So let's look at this graph on the left and let's sort of observe what the key features of this graph is, right? So all of these spectras are called Planck spectrums. And this is because these spectrums came from how he derived using the quantized theory of light. So let's look at the area under the curve, right? First, we're going to look at let's look at the 800 Kelvin spectrum. And the area under this curve is given by the Stephen-Boltzmann law. And let's give some intuition behind this, right? So if I look at this curve, on my y-axis I have energy density, which is sort of like my power, right? And on my x-axis I have the wavelength. So what if I'm taking the area under this curve, I'm looking at what is the total power that's given off at all the wavelengths, which is basically what Stephen-Boltzmann law tells me. It tells me what is the total power that's being emitted by my black body. Now let's look at Wien's law in relation to this graph, right? Wien's law tells me what lambda is my black body going to be radiating at the most? So basically, I'm looking at the peak of my Planck spectrum. So this peak, the top of my spectrum, is given by Wien's law. And other key things to notice about this graph is that the higher the temperature of your black body gets, the larger the area under the curve gets. And this makes sense because Stevens-Boltzmann law says the power is related to temperature to the fourth. So as temperature increases, my power also has to increase, which means my area under the curve must increase. Another thing you see is that at higher temperatures, my peak shifts more and more to the left. This again makes sense because T times lambda max needs to be a constant. Temperature and my max wavelength are inversely related. So the higher the temperature, the lower my max wavelength will be. Okay, now let's look at one of the experiments that sort of solidified quantum theory of light. And this was actually what Einstein won the Nobel Prize for. And so let's look at the photoelectric effect. What was the photoelectric effect? Basically, Einstein took a metal sheet, right, and he shined electromagnetic radiation onto this metal sheet. And what happened, right? What happened was electrons are emitted from this metal sheet, right? So this didn't really make sense unless electromagnetic radiation could be represented as a stream of photons. So this is how we're going to think about it. Electromagnetic radiation is represented as a stream of photons hitting this metal sheet. And what Einstein noticed is only when we had a certain frequency, only when we had a certain frequency of light, sort of like a threshold frequency, were electrons emitted. So no matter the intensity of light, no matter how bright the light was that was shining, right? No matter the intensity, we needed to overcome a certain threshold frequency. And this was really important. So each photon, right, is basically transferring energy to the electrons. And only a photon with a sufficient energy, greater than what we call the work function of the metal, can eject the electron. So let's now talk about what is the work function and what does that mean, right? The work function is the amount of energy needed to eject the electron from a piece of metal. So it's similar to like an ionization energy of an atom, right? It's how much energy do I need to eject this electron. And one of the key equations for the photoelectric effect is here, right? Half mv squared equals hv minus phi, where phi is our work function. And now what does this mean and how did we get it, right? H times the frequency is the same thing as the energy of the photon that's striking the metal. So this is the amount of total energy I have to deliver to my electron. So this energy must be equal to the kinetic energy of the electron, right? This is the energy that the electron has after it's ejected, plus phi, which is the amount of energy I needed to put in just to eject my electron. And this should make sense, right? This is sort of like a conservation of energy, and this is what Einstein found and noticed. And let's look at this graph to the right here now. Here we're plotting the frequency of the radiation on the x-axis and the kinetic energy of the electron on the y-axis. And we can see that each of these lines is linear, right? And this makes sense because if we look at this equation that we have here and we rearrange this, we have kinetic energy equals h times the frequency minus phi. The slope of this with respect to the frequency is Planck's constant. So we should have a linear graph, and that's what we see, right? And you can also see that denoted in the image there. So another thing you see is that we have different threshold frequencies for each different metal. And let's sort of reason why it's like this, right? So we have rubidium having the lowest frequency, threshold frequency, and we have sodium having the highest threshold frequency. If we look at the periodic table, we can see that rubidium is a much lower on the table than sodium, right? Which implies that it's also a much bigger atom than sodium. So we have in rubidium, we have the valence electrons more loosely bound to the atom because it's a much bigger atom. And this makes sense. This is consistent with our information because the frequency of the radiation that's needed to eject an electron should be less in rubidium because I need less energy to eject the electron since the electron is less tightly bound. And with sodium, it's exactly the opposite. It's the most tightly bound, which means it should take the most energy and the highest frequency radiation in order to eject the electron. Okay, thank you guys for watching. This is all I wanted to cover for today. And next time we'll delve deeper into more quantized nature of energy levels in atoms and go into the Bohr's model of the atom as well. Thank you again for watching, and I hope you stick with me and watch some more of my content. Thank you again. See you in the next one.